Hello there and welcome to another episode. In this episode, we're going to take a look at the voltage controlled switch and also another kind of voltage source called Piecewise Linear. So I'm going to start by placing a voltage source here, and I will be explaining what we intend to observe, right? And then, by the way, you don't always have to connect a wire from one point to another. You can always use the net labels to accomplish the same, okay? So, for example, I could just extend a wire from here to, let's say here, not because it matters, but like always, I'm pedantic and I like things to be linear and regular. All right, so this is my voltage source and I'm going to create a net label here. I'm going to call it VCC, and that's going to be an input, right? So I connect it here like this, and that means I can also connect the same net label here, and that essentially is going to connect this point to this point. So it's going to look like there's a physical wire connection between them, and we do this for neatness. Sometimes if your circuit is complex and a lot of wires are crossing, it becomes difficult for people to follow. So you can also develop the habit of using net labels to make your schematics cleaner. All right, so I'm going to put a ground here, and that is it. Now I'm going to bring in the component which is known as the voltage controlled switch. You search for SW like this and you place. Now I'm going to orient it such that it's easier for me to lay out things in the circuit. As you can see, there is a switch side of it on the right side, and then there is a negative positive connections on the left. I am going to rotate it. Yes, this way is better, and put it here so that when I turn on a voltage source, I will explain. Basically, this is how this switch works. You connect another voltage source between this plus and minus point, and then you can set a threshold for the switch that if it senses a particular voltage threshold here, then it should act like the circuit, the switch has been closed. Otherwise, it's open. It's as simple as that, okay? Now, if you are used to other kinds of circuit simulators where you can actually click on the switch to activate and deactivate it, this might seem like a needless complication, but don't forget that LTSpice, which is powered by the Spice engine, solves your circuit numerically. So it's different from those other kinds of simulators where you can actually click to activate and deactivate. So that is why you are using a voltage to close or keep the switch open, basically, and you are going to understand everything, so don't worry. All right, so I'm going to connect a wire from here to this point, and I'm going to extend a wire from here down here, and then I'm going to put a ground there, which essentially also connects that point to the ground. All right, so now we have this. I'm going to go ahead and then set the values for this. So let's say this is a 5 volt DC, okay, and we are going to pass a 5 volt DC through a 1K resistor, and we want to see the current that is going to flow. But as you can agree with me, no current is going to flow until this switch has been closed, right? So we have to put another voltage source here to control when the switch gets closed, and then we can probe around to see that indeed this switch here is voltage controlled. To do that, I am placing another voltage source here, V2, okay, and what's going to happen is I'm going to put a wire. Again, you don't need a wire, you can use a net label, but just so it's also easier for you if you are new to this whole net label stuff. and you connect the grounds to ground. I can hook it straight up to this ground here, or I can also just do it this way. It doesn't matter. I could have connected directly to this ground here, but I'm just separating it for maybe it helps some people to understand things better. All right, so now we have a voltage source that's gonna control when this switch gets closed, right? So we need to configure this voltage source, and this is where we get the opportunity to learn about piecewise linear. So I'm going to click on advanced. The last time we looked at pulse and sine, and I said we'll look at the other ones when it becomes necessary. Well, today it's necessary for us to look at piecewise linear. As you can see from here, this is a voltage source that helps you to control precisely each time step and the voltage that it should output. All right, so I'm going to say on 0th second I want the voltage to be 0, and on the 5th second I want the voltage to be 0. Now just a brief moment after the 5th second, so I'm going to do 0 0 0 0 0 0 1. So this is a very brief moment after the 5th second. I want that voltage to go to 5 volts, and you don't have to fill in for all of these. It's going to keep what is the last voltage unless you change it. And if you need more points, you can click on additional PWL point. PWL stands for piecewise linear, and you can also browse to a file where you have already defined this. So if you have some signal already defined, you can browse and select it. So I click this, and so this is the configuration for this particular voltage source. Right now we aren't done yet. We need to configure transient analysis, and mind you, I need to configure things to be at least something above 5 seconds, because we've configured this power source to turn on at the 5th second. So if we set our stop time earlier than that, we won't get to observe what we want. So I'm going to go with the value that I like the most, 10 seconds, and I'm going to place it. It doesn't really matter where I put it, but I'm going to place it here. Again, we aren't done yet, and to prove that, I'm going to run this so you can see an error. Yeah, it tells you undefined model SW blah blah blah. Hard to understand, and this is why I'm here. I'm going to explain that to you. So we need to modify or control or code the model for the switch. I'm not going to go into too much details in this particular video. I will have a dedicated video after this video just to talk about the voltage controlled switch and its parameters. But for now, to get it to work, you need to add a directive called .model, and the first one is you need to give it the component designator so that it knows what you are controlling. Our designator is SW, okay? And then the model itself is also called SW. Don't worry about this now. We just need to place this here so we get it to work. I will have a dedicated video on setting the different parameters for the voltage controlled switch. So we put it somewhere close to the switch. So I'm gonna put that here. All right, so now this is a very simple circuit, right? We have a 5 volt connected to a 1K resistor, and there is a switch, but that switch only turns on after the 5th second. So what it means is we expect that when we probe for current going through this resistor, it should be 0 until after the 5th second. When the switch is closed, then we observe that current indeed is going to flow in here. All right, so let's simulate that. All right, so we can probe around. If I click here, I expect to see a constant DC 5 volt, and this voltage source is different from this. This one is controlling the switch here. Let me zoom in a bit. This one is controlling the switch here. So this right from the 0th second is outputting 5 volt. Fantastic. And because this point is electrically connected to this point, if I probe here, you see basically the same thing. Now let's probe the current that is going through this resistor. And as you expected, you can see that no current was flowing all the way until after the 5th second when 5 milliamps started flowing. And it's 5 milliamps because of Ohm's law. V is equal to IR, so I is equal to V over R. So if I divide 5 by 1000, I get 0.0005 amperes. Okay, so that's why it is 5 milliamps. But I want you to focus on what this voltage controlled switch is doing to your simulation. It ensured that in the simulation, no current flowed through this resistor because the voltage that is controlling this switch is defined to turn on only after the 5th second. In fact, I'm going to add another plot here. So I'm going to add another plot below the pin, this one, and I'm going to probe at the voltage that comes here. And look at it. You can see that the current, so up here in blue, is the current that is running through the resistor. And you can see that it follows the activity of the voltage across the switch because we used a piecewise linear, and we said that, again, we can look at it here. On the 0th second, it is 0 volts. On the 5th second, it is 0 volts. So what it means is between the 0 second and the 5th second in the simulation, there is 0 volt across the switch. All right. And then just a brief moment after the 5th second, so I did 5.00000001, and then I said the voltage should jump to 5 volts. So what it means is that it's only after the 5th second that there is going to be any real voltage across the switch. So think of the switch as a switch that some way somehow senses the voltage across it, and if the voltage is above some threshold, it closes the switch. I said some threshold because we can precisely control the threshold it should sense before it closes using this dot model here, but I'm going to leave that for another video. So if you don't set any voltage threshold, then what's going to happen is the moment it senses any voltage above 0, it's going to close the switch here. Hence the observation we are seeing here. I know, like I said earlier, if you aren't used to this kind of thinking, it's difficult to wrap your head around it, especially if you are coming from simulators where you can interactively click on the switch to close and then click to open. But remember, LTSpice is powered by Spice, and Spice solves your simulation linearly. Numerically. So it's doing numerical calculations to come up with the simulation. So you lack that interactivity. Thank you very much for watching. If you have any challenges understanding this, please ask your questions and I will avail myself to answer. See you in the next episode.